So the next talk is by Andrei Sobolevski from Moscow, and the title is Les travaux de Michel Hénon en algorithmic.
Well, thank you very much. I think that for the purpose of this talk, probably I'm coming not from Moscow but from Nice, because the subject about which I'm going to speak and our collaboration with Michel, which took several years, roughly 10 years ago, was in the context of something that I was doing as a postdoc in the Observatory of Nice. And a year before, when we started with Uriel Frisch, who is present here, when we started working on the problem of cosmological reconstruction. But the aspect which I would like to touch in this talk here is this. We know that Michel's contributions were crucially important, and they shaped a few fields of modern mathematical physics and mathematics. I mean, his scientific personality was so immense that actually even his secondary contributions, minor contributions that didn't change full field, they still bear a lot of information about his personality, and it is interesting to study them in their own right, to learn something additional about Michel. So this topic on which I'm going to speak here is his one, I think, can say his fascination with analog computers, with devices which, through some physical process, happen to solve a mathematical problem. Usually devices that are constructed for a specific mathematical problem at hand. And this is something that Michel did several times in his career, probably more than I am aware. And one of these examples, I know it quite well, and I will spend most time in my talk explaining it. So if you do a Google Images search for analog computers, you find lots of interesting stuff, of course. But scrolling this web page, you find something which doesn't quite look as a computer. You find this picture. It's a screenshot of a search that I made yesterday, so probably it's still there in the same form. This is actually a figure from a 2003 paper of Roy Mohoyai. Here we can see it in detail, which illustrates one of these analog computers invented by Michel for the purpose of solving a problem in mathematical programming, which is called the transportation problem. Now, just to put it in a bit of a context, when we were discussing this, our presentations for this workshop with Fatina Mouni from the Observatory of Nice, who is going to talk tomorrow afternoon, it turned out that one of the first, if not the first, research publication of Michel, an item in Compte Rendu in 1955, also concerned an analog computer, this time not mechanical but electric, for solving a specific mathematical problem, for performing a specific kind of integration in theory of complex variables. Then, when Michel started working in Institut d'Astrophysique de Paris here, in his thesis he employed another analog computer which was implemented, I mean, is a real physical system experimentally for integrating differential equations, but the model, the mechanical analog computer which I'm going to explain here, it was never actually built as a physical device. It was rather mental, and it provides an interesting way of intuitively thinking about a certain mathematical problem, which I'm going to explain. So the computer itself consists of two sets of bars. Oops, sorry. I tried using a pointer. So two sets of bars, which are constrained to move in vertical direction while preserving their horizontal position in space. So every bar, I mean, one set, I will call them upper bars. They go in the direction of the y-axis. The other set are orthogonal to them. Upper bars have weights, have forces that move them downwards. Lower bars have, negative weights or buoyancies, so they're constrained to move upwards. And also there is another feature, which is these small studs of negligible weight, which are fastened to lower bars, and they prevent, I mean, each stud prevents a specific pair of bars from coming too close. For example, this stud prevents the second lower bar from coming too close to the first upper bar. Now, if we release this system and put it into motion, bars will start moving. They will start, I mean, studs will start touching the bars. Aggregates of bars will form, which will be in contact through these studs. And finally, the system will set into an equilibrium state, which will obviously have the property of minimizing its potential energy. This is obvious from, I mean, for any physicist. But the point here is that at the same time, this solution, this equilibrium configuration, will maximize a certain quantity, a certain quantity which has the meaning of a cost function or utility function in a certain optimization problem. And I mean, let me just I mean, to fix the ideas, let me just introduce some notation. So for the variables describing the geometrical configuration of the system, we take heights of the two sets of bars, studs which correspond to geometrical constraints on configurations. They will be denoted Cij for a stud which prevents bar I from coming too close to bar j. And then, in order to equilibrium to be well defined, we require that the sum of weights should be equal to sum of buoyancies. Therefore, the system can, in principle, settle in equilibrium. And the potential energy of the system is then given by this expression in terms of weights, heights, buoyancies, and heights of lower bars. Now, when a pair of bars is makes a contact through a stud, they exert a force. I mean, the stud transmits a force Fij, with which they contact one another, and finally, when the system settles in equilibrium, the equilibrium configuration in it, these forces exactly compensate weights and buoyancies of bars. Therefore, I mean, for any feasible configuration of the system, we have that geometrical constraints and I mean, positivity of forces mean that products of this kind are positive, and therefore the potential energy is always greater than this quantity, which combines forces and heights of the studs. In equilibrium, either when a pair of bars is not in the contact, then the corresponding force is 0, and if they are in the contact, then this expression is precisely 0 because the vertical separation is precisely given by the height of the corresponding stud, and therefore in equilibrium it turns out that these two quantities, the mechanical energy and this linear combination of forces, precisely equal one another, whereas for any feasible configuration there is an inequality relating the combination of forces is always not greater than the mechanical energy. Therefore, in the equilibrium configuration, the mechanical energy coincides with the maximal value achievable for this quantity here. Now, this quantity can be seen as a utility corresponding to a certain distribution of forces in which part of buoyancy of J's lower bar, precisely Fij, is transferred to compensate the corresponding part of the weight of the upper bar I, and Cij is the weight associated to this force. Therefore, any distribution of forces, the utility of a distribution of forces is, I mean, therefore, this combination corresponds to the utility and the equilibrium state of the system automatically leads to maximization of the utility function. Now, this problem I mean, it recurs in Michel's work several times, and the first occasion on which he thought of this model was actually very early in his career, even before he started his work as a researcher. The first instance when when this model was invented was still in his pre-university years, when he was thinking about the problem of finding an optimal class schedule in a school, which led to a manuscript of 1950, and I was very much impressed, and when we were discussing this maximization problem with him in the context of the cosmological reconstruction work, It turned out that these nodes, he was able to locate them in his archive and produce a copy. In these nodes, he considers a problem in which bars correspond to professors and classes. And actually, the utility of giving a lecture of this or that professor to such and such class the problem is to find a distribution of classes which would be optimal from the point of view of convenience for both professors and students. In this case, the utilities, the parameters Cij, they are kind of discrete. They are correspond to convenient and inconvenient arrangements. I mean, I don't feel very well today. Sorry. No, that's fine. Thank you.
Are there some questions or comments? Or?
Probably, yes.
In the afternoon.
Yeah.
In the afternoon about this.
Okay, so Uriel said that this afternoon he will say something about that. So if not, thank you.